my pleasure to introduce Jacopo De Simoi from Paris 7. He will tell us about Birkhoff conjecture and spectral rigidity of planar convex.
Thanks a lot for the opportunity to be here. It's nice to be in Brook. The first time, actually. So what I would like to talk about today is its recent results towards Birkhoff conjecture, which is something we'll state shortly, which is related to billiard dynamics, and the implication that we found to be useful on the problem of spectral rigidity of convex planar domains. So let me just introduce in a very broad way what I mean by billiard dynamics. Billiard dynamics is, again, very broadly the study of geodesic flow of a manifold with a boundary. Now, for the purpose of this talk, I will restrict myself to a very special situation. So I will consider the domain omega to be a subset of R2, which is compact, strictly convex, and we consider the Euclidean metric on R2, so I just have a flat structure of this set, and I assume that the boundary of omega is a sufficiently smooth curve for instance, C3 will be enough for stating the problems, or with more smoothness later on when I can state the results. So what is a billiard? Your favorite convex domain. And then you have a unit mass ball which travels inside with unit speed. At the moment at which the ball hits the boundary, you use Fermat law to continue. Fermat law says just that the angle of incidence is equal to the angle of reflection. Speed doesn't change. When you keep moving along inside the billiard with this specification of the dynamics. So in billiards, it's typical to study what is called the billiard map, which is a discrete time description of the continuous time description which I just drew on the board. And so what one does we need to record, we need to pass to a concrete section, and we need to record some information. And information is interesting whenever we have a collision. I mean, during the free flight, nothing really changes. So what we need to record will be the point at which a collision happens. So let's fix an origin of my domain, let's fix an orientation of my domain. Let's take a parametrization of the boundary, which I will denote with S. S is going to be arc length. So I will say that the collision happens at the position S, like here, and with angle phi, and phi is just the angle of the outgoing trajectory with the positively oriented tangent. So in this case, it will be this angle over here. And the map will map this collision point to the next one. So if I start considering the end collision point, then the map will map it to the n plus first collision point. So if this is Sn, Pn, the next guy will be this guy here, Sn plus 1, with the angle, again, Pn plus 1. This map is called the billiard map. I will denote it with big F, capital F. And it is a map from the phase space, which is just the product of the boundary of omega with the possible angles that I can have. So 0 to pi open, and this will map this the phase space I will denote it with curly M. And okay, fine. This is a very nice map. It has nice properties. It's a twist map which preserve area given by sine of phi ds d phi. And the goal of study of linear dynamics is to understand the long-term behavior of this map. So there are two paradigms when we want to describe long-term behavior. There is a quasi-integrable paradigm in which the dynamics is somehow restricted to invariant subsets of lower dimension. A lower dimension, in this case, we will have invariant curves. And the other paradigm is when the dynamics is chaotic in some sense. Positive atomic exponents, positive entropy, sensitivity to initial conditions, and all this sort of stuff. So again, what we want to do is to study for a given billiard table, for a given domain omega, what is the resulting dynamics. And in order to do that, let me start from a very, very simplified, non-typical, extremely non-generic example. I will take my domain to be just a unit disk. And for this system, we can pretty much write down everything. First, so what now F is just a measure, so it's a unit disk, so it's going to be just the phase space is going to be 2 pi S1 if you want times 0 pi, and the map will simply map SP to, let's have a look, if they start with the point S with angle phi, I will end up here with the same angle phi, so the dynamics of the phi variable is quite easy. So this is going to be mapped to phi, and S will just be increased by 2 phi, and it's just elementary geometry. So F, in the case of the circle, I write down what it does from my phase space, which is this guy, this is M. So F, we preserve the constant the foliation with y equal to constant. So if I take, let me define gamma omega to be the set of points, so that 2 phi is equal to omega. Omega is going to be the rotation number of the map. So any of these curves which foliate my phase space will be invariant by the dynamics. And the dynamics on each of these invariant curves is just a rigid rotation by angle omega. S plus omega. So this is a case in which we have foliation with such invariant curves, and the map is actually a rigid rotation on each of them. So you have that the phase space M is given by the union over all rotation numbers omega of gamma omega, and again F restricted to each of these guys is S max to S plus omega, rotation by omega. Now this very simple picture justifies the definition of an invariant circle. So we'll define a curve gamma curve in phase space. It's an invariant circle. If it is homotopic to one of the boundary components of my phase space, so to phi equal to 0, for instance, I can take it closure to my phase space, and of course it is invariant. But then it's easy to define the rotation number of F restricted to the invariant curve, which is just, okay, fine, this is invariant, so, and it's homomorphic to the boundary component, so this is just a map of a circle, and then you can lift it up to the real line, and then you can compute the average drift of f, that is the rotation number. So to given a curve, you can an invariant curve, you can associate the rotation number, and this will be called the rotation number of the invariant curve. It's independent on the point, and it will be denoted by omega. So we have the definition of an invariant circle. And there's a very nice property of invariant circles for twist maps, and in particular for the billiard map, which is due to Birkhoff, is that if gamma is an invariant circle, then it is a Lipschitz graph over the cyclic variable s. So it is given by S, P of S, where S belongs to the boundary of M, where P is Lipschitz. What does it mean?
Being boundary of omega.
I am being boundary of omega, absolutely. So what does it mean if I have an invariant circle for my map over here? This has to be a Lipschitz graph, so it has to do something like this. And for any point down here in the base, I can find a unique angle over there. Now, if I go back to the picture for my convex domain, what this means is that for any point on the boundary, I can find an angle. If I draw this set of lines, I will find that we have an envelope, which is a curve which is tangent to all of these lines here. And this envelope is called the caustic associated to gamma, and I will denote it by gamma hat. It has a very nice property. By invariance of gamma, it is so that if I shoot from any point on the boundary with this angle that is tangent to this curve, the next bounce will also be tangent to this curve, just by the definition of invariant curve. And so this is indeed a caustic in the Greek sense, so it's a curve which will get very hot if this were a ray of light. And this also allows me to give a definition of a convex invariant circle, so omega is said to be convex invariant circle if gamma hat is a convex curve. It's a convex curve in my domain. It's actually easy to construct billiard tables, analytic billiard tables, which have non-convex caustics, so caustic which have cusps. Take any constant width domain, then caustic corresponding to the equator of the phase space would actually have cusps, unless the domain is a circle. So easy thing to check. So okay, so far so good for the definitions. Now, the situation for the circle is quite peculiar. One can ask whether or not these invariant circles are something which happens just for the case of the circle because we are such a special situations, or if they appear often. And in fact, that is the case in some sense. So there's a theorem by Vasutkin in 1976. And the theorem originally says the following: if the boundary of omega is smooth enough, exists a positive measure set of invariant curves for F. And those guys accumulate to the boundary. So in other terms, I can find, provided that the domain is sufficiently smooth, I can find a counter set of invariant curves whose density actually approaches 1 as they approach the boundary of M. And if we translate that back to caustics, those are caustics which are very close to the boundary. And this result is by the Zutkin to show that if you have a convex domain sufficiently smooth, then it cannot be ergodic because we just have caustic closing after the boundary. We said that if you start sufficiently close to the boundary in the sense that you take sufficiently small angle, it will keep there forever. You cannot cross these things. It will always be tangent to.
What does the hypothesis strictly convex mean? Do you mean non-zero curvature?
Yes. If you allow zero curvature at just one point, you might have, you might find an example which has no caustic whatsoever. So strict convexity means precisely that. So this theory was later on improved by Raphael Guadi in his thesis. Which brought it down to a more reasonable 6, which, okay, fine, then you can debate if this is optimal or not, but I'm not getting into this kind of business. And the proof, I just want to mention that the proof relies on K-M theory, which you could guess from these crazy assumptions. So essentially it boils down to find a good coordinate system in which the system is close to integrable. Integrable means the circle. And then if you perturb this in some way, and the closeness of the perturbation gets better as you go closer and closer to the boundary, and the perturbation is smooth enough, then you can show that most of this story persists, and you know the story. So the question is, okay, fine, we have a positive measure set of curves which are invariant, but this is something which doesn't still describe the dynamics fully because in the case of the circle, for instance, you have more than that, or way more than that. So let me throw in a definition. We say that the billiard table omega is integrable if the following happens. You take your invariant curves, take a union over all invariant curves, invariant circle actually, and then you want to ask that if you take the interior of this guy is not empty. In the case of the circle, this is clearly true because the interior of, because this is the whole thing. So in particular, since invariant circles foliate the whole space, the disk is integrable, which is good.
Yeah, I think you should switch the chart to this one on the page.
Okay, sorry, I guess I missed it out at some point. So is this fine for you? But there's another notable example of integrable billiard, which is an ellipse. So ellipses are also integrable. And the phase space of the ellipse is not as in the case of a circle foliated by invariant circles, but the picture is something like this. So you have this special trajectories there, which are the ones who will cross the foci of my ellipse. And this special trajectory will separate some invariant curves which are not circles because they are contractible from invariant curves which are circles because they're not contractible. And we are only interested in these guys for the definition of integrability. And this is definitely an integrable system because you have a large portion of phase space which is covered with that.
So could you draw the picture of the ellipse of the first one integrate?
So here are the foci. So for example, the dynamics on the separatrix of this picture would be as follows. So that ellipse has the remarkable property that any trajectory to one focus will hit the other focus after one reflection. And so what is this numerical simulation telling us? It's that the dynamics will converge to an orbit which is bouncing back and forth along the major axis, which is this point here. So the dynamics is actually doing something like that. So you have, these are fixed points for the dynamics, and you will bounce back and approaching this point exponentially fast. In fact, it's in a hyperbolic fixed point. On the other hand, if you start close enough to the minor axis, you will get something like this. And orbits will be confined between two arcs of a cofocal hyperbola. And the caustic corresponding to these guys are the curves which are not circles here.
This happens for one trajectory on the circle.
Pardon?
This kind of thing happens for one trajectory on the circle. The one that goes through the center.
Well, that is a very degenerate trajectory because
But it would be like a point.
it will be a point, yes. And if you start from any other point in the phase space, you would get. So if you hit the major axis on the outside of this 6 segment bounded by the foci, you will get so-called outer orbits which correspond to this guy. And then you will keep hitting. Hitting your major axis outside of the foci, and the invariant curves would then be cofocal ellipses. Now the picture is getting extremely messy. But for each of these invariant curves, there is an invariant cofocal caustic ellipse, which is a caustic there. So invariant circles foliate a piece of the plane, and in particular their interior contains an open set. I mean, the interior is non-empty. They contain an open set. And this is the usual definition of integrability. There are various definitions of integrability, and this is the most general. So, okay, we have an example, the circle. We have another example, all ellipses. And the question is that it? This is in fact the content of Birkhoff conjecture. So the study of billiards was originated by a seminal paper by George Birkhoff in 1927. And this conjecture is usually attributed to him, although there's no mention of it in any of his papers. There is a mention of it in a paper by Paritsky. Paper is dated 51, and the story is actually quite funny. Paritsky was an immigrant from Belarus, And he got his, he studied at the high school in Bronx, and then he went to Cornell for his undergrad and PhD. And as soon as he got his PhD, he got appointed with National Research Council Fellowship at Harvard, where he met Birkhoff, and he worked there for a couple of years on this. And then he got a position, a permanent job at GE General Electric, and he got the job there as a consultant. And after 30 years, he publishes this paper on the Annals of Mathematics, in which states this conjecture. The only integrable billiards are inside ellipses. Is usually attributed to Birkhoff, I don't know on which grounds. There's a footnote in the paper by Paritsky which says that all of this work was obtained while being a postdoc fellow, essentially, at Harvard in 1970.
Possible, as long as there's no evidence.
Actually, I spoke to Paritsky's grandson a couple of months ago. He happens to be a faculty in Toronto. And there's no, he was, of course, interested in this. And he has no idea whatsoever.
Birkhoff was still alive when he published it?
Good question. Should check.
Paritsky, the grandson, is a mathematician.
Yes. It's with an analysis. Okay, so, this is a conjecture. And I would like to but this conjecture is wide open. There's no clear way to think of proving that. What I would like to tell you is a partial result, which we obtained. Under a condition which is related to that, I will write it down. I will write the condition which I will call strong rational integrability. So omega is strongly rationally integrable if the following happens. If the union over all invariant circles, all the invariant circles, take the interior, and we ask not only that it is non-empty, but that it contains a set of invariant circles of rotation number 1 over q for all q larger than 2. So these are invariant curves, invariant circles of rotation number 1 over 2. So we need this condition. To be honest, we need a weaker condition, which, as you can guess, is called rationally integrable without strongly. But to define it, I need to talk a little bit about periodic orbits, which I will do in a moment. But for the time being, let me state it, assuming the stronger version of our, assuming the stronger version of the hypothesis. The theorem.
And you really need 2.
Pardon me?
You really need 2.
Yes, and well, you can see why this is true, because even for an ellipse, the caustic of rotation number 1/2 is kind of singular, because it's given by the union of this. It's given by the union of these things. This part. This is the caustic of rotation number.
It is not enough for you to have sufficient disputes.
Unfortunately, not.
I'm not familiar with this fractional rotation number. Can you just say what that is?
Oh, well, okay. Well, let's say that it contains a periodic orbit of period 1, which winds only once around the domain. So for instance, this is your convex domain. Something like this would be a periodic orbit of rotation number 1/4. There's a period 4 and it winds only once around the domain. Actually, the condition that this is contained in the interior of the set of all invariant circles implies, that's really what we use, that not only this guy contains one of these periodic orbits, but every point on this curve is a periodic orbit of this type. This is actually what we use. We use that we have, for any q larger than 2, invariant circles which are convex and given by periodic points. That's the weak rationally integrable condition.
So there just has to exist one of these.
No, the set of all of them.
Oh, I see.
I want all of them.
But there, one of those in the curly parentheses.
Yes.
That's what I mean.
That is one invariant circle, which is an invariant curve. Which
So
is
you're saying that if you start at any point, you get a four-sided figure.
If this is true, yes. But in general, no, because for instance, in this case, you don't get any periodic orbit except if you start right here.
Yeah, no, I'm just trying to understand what the condition means. So that gamma sub 1 over q means if you start at any point on the boundary, you go around, you hit q times and you go around once.
Yes.
At any point on the boundary.
Yes. Yes. That is, and I want this for any q, for all q larger than 2.
So just consider circles is conjugate to the rigid rotation, the rotation number 1 over 2.
Yes, another way of saying it is exactly as Misha says. If you lift it up and you take the qth iterate, then it's just going to be a translation by time. Okay, so the theorem, which is joint work with Artur, Avila, and Vadim Karoshi, 2015, says that I'm going to state it with all the epsilon and deltas. So there exists E naught and epsilon naught positive so that for any for any E naught and epsilon less than epsilon naught, every strongly, but maybe not rationally integrable omega, which is C39, apologies, close to an ellipse of eccentricity, epsilon C39 close to an ellipse of eccentricity E. So you have domain which is close enough, some sense, to an ellipse of sufficiently small eccentricity. It is rationally integrable, then is an ellipse.
So if it's just almost like a circle, then you can conclude it's an ellipse if it satisfies.
Well, the point is that why do I need these two things and insist on that is that E naught is probably 1/3 or something, and epsilon naught is out of control. So you can really say something about stuff which is close to ellipses of reasonable eccentricity, but you can control how close you have to. I mean, you could, but that's the reason why I have.
When you say out of control, you mean it's It's not.
I mean, you have to follow through it's not constructible, whereas the condition for eccentricity is in principle checkable.
So you mean that your method gives explicit estimates on Pelmont and so on?
No, not explicit.
Not on this, but on that. You essentially need to check if some matrix is inverted. You can see it with the computer and see if you have a good undergrad student. So this is the result which I wanted to talk about regarding Birkhoff conjecture. And now I would like to slightly step aside from this, but not too much, and talk about the problem of spectral rigidity on convex planar domains. And to our excitement and surprise, we found that tools that we developed for dealing with the Birkhoff conjecture proved to be quite effective in the study of the problem of spectral rigidity of these things. So let me
Can I
do the brief.
just before you jump?
Sure, absolutely.
I just want to know, so is this KAM type mathematics? Or just maybe vaguely related or not at all?
So the C39 business is not KAM related. The only part of KAM theory which we use is that we rely upon this very nice coordinate system which Zutkin used to prove his KAM result, which needs 6 derivatives. So whatever that 39 is larger than 6. And in this bound, yes, it is a KAM result.
So you use that for the existence of some curves.
Yeah.
And after that,
Well, not quite. We use them because those coordinates are particularly convenient. In this case. And you can define them and they have nice property provided that the system is that the map is multi-enough. And you need that C6. So that is the end of KM. And then the C39, if you're very curious about where it comes from so it's clearly an artifact of the proof. I don't think it's so. Huh? You don't think it's so? I don't have any. I mean, C6 might be shy.
Is it like a structural stability type of thing that you have?
It's really an artifact of the proof because what we do is that at some point we so how do we prove this result? We prove an approximation scheme. We prove the following approximation scheme. You're close to an ellipse and you're rationally integrable. Then, if this is true, you can move your ellipse a little bit and find another ellipse close by, which is a better approximant of your domain. Now, this clearly leads to a contradiction because if you have a bounded domain, there's an ellipse which best approximates this in any CR norm. So if you apply this approximation lemma to that optimal guy, you will find that indeed the optimal guy is the domain. The problem is that when we do this, the approximation works not in C39, but works in L2. So you show that the L2 norm becomes smaller than the C39 norm at the beginning. And in order to upgrade the L2 norm to C39, whatever you need some kind of Sobolev embedding type estimate. And in order to get that, you need enough derivatives to kind of play around. And we need 39.
So the functional that you're minimizing is sufficiently nonlinear that you need many derivatives? Is that how you should think about it?
The functional...
I mean, you have this family of ellipses living in some much more general space.
Yes.
And you're measuring a distance.
Yes.
That's some nonlinear thing. That's why you need... Because Sobolev embedding theory in itself doesn't require...
No, it does not. But if you have a bound on... Okay, fine. The point is that the approximation that we get, it's some kind of... you start with something of norm epsilon, and you get something out of which is better approximated in the sense that it is of norm c times epsilon to some power greater than 1. Okay? And if you don't want to lose that thing, you need to get very fine Sobolev estimates. In order to get very fine Sobolev estimates, you need to get very smooth, you start from very smooth functions. It's clearly an artifact of the proof. We don't play in sharpness, but that's what it is. 39 derivatives. Well, still better than 553. Okay, so let me start with describing a little bit of the problem of spectral rigidity for these kind of domains. So I would like to just give an idea of periodic orbits as a solution of a variational problem. Which is the following. So I take my favorite convex domain, and I take Q points on it, and I join them in some order. 1, 2, 3, 4, 5. And I want to compute the length of this object here. So I'm going to take LQ, which is a function of my domain omega, and a vector S, well, S naught up to S Q minus 1. In this case 5, which is just given by the length of this, so I just sum up over the length of the edge connecting SK and SK plus 1, K from 0 to Q minus 1. And it is a fact, which was again observed by Birkhoff, that critical points of LQ correspond to periodic orbits for the billiard.
Would this still be true if you use squared length, or is that false?
Pardon me?
Suppose you use squared length instead of length, L2. Would that still be true?
If I do what? Pardon me?
If you sum the squared length.
Yes. I believe so. Yes, it's actually easier to state problems. The point, yes, it's absolutely true, because what is the gradient, or what you have to do, you have to put the gradient of this guy equal to 0, and the gradient of this guy is equal to 0 if and only if, well, if you move this point along the boundary, the length or the square length doesn't change, and this can only happen if this angle is equal to that angle. So absolutely yes. And this is a very nice property, because it allows to find periodic orbits just by using the maximum time, the fact that any continuous function is the maximum. And in fact, it was used by Birkhoff to prove that you can cook up a periodic orbit for any rotation, any rational rotation number. And in fact, Birkhoff used it to prove that you can actually cook up 2 periodic orbits for any rational rotation number. One is the max of this function, and the other one can be obtained by minimax type arguments. That is, okay, fine, this is a nice maximal orbit, then what I do, I take S0 here, and I slide it until I get to S1, and when I get to S1, I get the same orbit, so we have the same length, and in the process, I will find the minimum of my L. This would be again a critical point to give me a different periodic orbit. So in fact, Birkhoff proved that you can find for each prescribed rational rotation number, you can indeed find 2 orbits of that rotation number. Now this is nice, it's very clever, and it gives a nice, allows us to give a definition. And we define the length spectrum of a domain as the set of all lengths of periodic orbits or closed geodesics, depending on what you want to some perimeters if you want perimeters. Periodic orbits. And then we actually want this set to be a closed set. And if you are living in a convex domain, you can find orbits which are closer and closer to orbits which bounce around a very small angle around the domain. And in limit, when the angle goes to infinity, you will just get the perimeter of your domain. So we either take the...
You say this perimeter, does that mean you throw away the red segments that are...
Yes, I'm taking my ball and I kick it tangentially so it will roll around. This still counts as your desiccant.
No, I guess what I'm...
No, but are you saying LQ
just outside of the star?
When you say the perimeter, do you mean L sub Q or do you mean...
I mean L sub Q. L sub Q of any.
That's not what we call perimeter.
Okay, so let me just write length.
That's better.
Length.
That's okay, I don't mind. I just want to know.
Length of the periodic trajectory. Because if I take length of the periodic orbit, then it's a period. Okay, length of the periodic trajectory. And again, I want this set to be closed, so let me take the union with the perimeter of my domain, which I will just denote by L sub omega. And I want to count this with multiplicity. We get n. Like that. So this is just a definition. I take the length of all possible periodic orbits, trajectories in my domain. I throw them all in the same set, and I get the set which is called the length spectrum. Now there's a very nice question which you can ask, which I call the inverse dynamical problem, which is the following. If you know...
So here when you're putting it multiplying by positive integers because you want to imagine going around a particular trajectory many times.
Yeah. So if we know the length spectrum of omega, can we reconstruct omega? This question has an obvious negative answer, because if I rotate omega, I get the same length spectrum. If I translate omega, I get the same length spectrum. So is that it? So modulo isometries. So if I know the length spectrum, can I tell what the domain is? Oops, keep that. Actually, let me do this. Same thing. So this question is very closely related to another very similar question, much better known. When you hear the shake of a drum, that is, let us consider the Laplace problem inside omega. So I want to find the solution of the Laplace equation, summation of u plus lambda squared u equals to 0 with some boundary conditions, for instance, u equal to 0 on the boundary. So I can find eigenfunctions, and these eigenvalues will form the spectrum. It might have multiplicities. And the question of cut is, can we reconstruct omega if we knew so this is called the inverse spectral problem. If we know the spectrum of the Laplacian of omega, can we get omega modulo isometries? This question was open for a long time, at some point some counterexamples started to surface in the realm of high surfaces with negative sectional curvature. It was in the 80s, and by Sunada, Vignera constructed some examples. And for domains in R2 with the Euclidean norm, the counterexample came much later, but it came eventually. And in general, you cannot hear the shape of a drum. And in fact, this is due to Gordon, Webb, and Wolpert in 1992. They constructed, I'm just drawing some random domains here, but the idea is they constructed non-isometric domain, which are very simple. They are straight lines, maybe with 8 possible orientation, 8 possible angles, which are isospectral but not isometric. And the idea is precisely to study the billiard mapping here and glue. Well, if you study billiard mapping, you can do some gluing, and if you glue the right sides of these things together, you get the surface of negative curvature, which is pretty much what the other guys found.
It makes the shape convex.
No. You cannot make the shape convex, and you cannot make the shape analytic. That is question: can you find convex analytic domain for which? Can you prove this for convex analytic domains? The answer is, well, almost. Zeldich, 2010, proved, as in very nice paper in the Annals, proved that among the class, so if you pick omega prime belongs to some class of symmetric, so axially symmetric analytic domains. Axially symmetric just means that you have one axis of reflection, and the domain is invariant for that reflection. So there exists a class of these guys, which is a generic class among symmetric domains. So there exists a class of generic axially symmetric. It's hard to know where to put it. Generic axially symmetric analytic domains, so that the spectrum of omega is equal to the spectrum of omega prime, then omega is equal to modulo isometry to omega prime. So in fact, if you restrict to axially symmetric analytic domains, you can hear the shape of a drum. Now, what is the relation with my problem over there? What is the relation with length spectrum?
So what is generic in this case?
Generic means
You have to throw away a few. Now,
I know what generic means.
generic means that you don't want to have two different periodic orbits with the same period, with the same length. And generic means that if you study the billiard map along every such periodic orbit, that billiard map is not degenerate. If you can find the Birkhoff normal form, the Birkhoff normal form is not degenerate. So it's a very explicit thing. What is the relation between these two words? Well, if you think of the one-dimensional problem, if you have a Laplacian on the segment, what are the eigenvalues? The eigenvalues are related on the square root of the length of this segment. So the same thing, and what is the length of the segment? It's the length of the only orbit that you have in a one-dimensional billiard. So there is a thing which relates the spectrum of the Laplacian and the length spectrum in general, and there's a bunch of people involved, Colin de Lapierre, Chazarin, Nardini, and Dustenmark. Anderson and Melrose actually proved proved in 79 for convex domains, strictly convex domains, that if you take this singular support of t maps to some a from 0 to infinity of e to the power lambda k e, that's in general singular distribution. If you take the singular support that is contained e plus or minus the length spectrum of omega and maybe 0, and under the hypothesis of genericity, which I didn't state but I mentioned before, this is actually important. But there's a very strict relation between the two. And in fact, any example that is known is so that any counterexample to this question is also counterexample to that question. So what is spectral rigidity? Well, something slightly weaker, relatively substantially weaker than the inverse spectral problem. Since we have counterexample, we kind of need to give up something. And what we give up is the fact that we don't want a global result. We are okay with a local result. With a local result, we say that omega is dynamically or just spectrally rigid if any C1 smooth deformation of omega that is isospectral means that in the spectrally rigid case, the Laplace spectrum doesn't change. In the dynamically spectrally rigid case, the length spectrum doesn't change. So any C1 smooth deformation of omega, which is isospectral, is isometric. So omega is spectrally rigid if you cannot deform it in a C1 smooth way to something having the same length spectrum or Laplace spectrum, unless you translate it or rotate it.
Are you making a statement about dependence on a parameter here?
Yes.
So you have a family of...
So I have omega t is a family t in some open set. And if the length spectrum of omega t is equal to the length spectrum of omega naught, which is equal to omega, say, we say that omega is spectrally rigid if this implies omega t is isometric to omega naught.
Or the statement would be for all t.
For all t in a sufficiently small neighborhood, yes. Yes. And so the conjecture by Sarnak is that any omega is spectrally rigid regardless of, well, any omega is smooth enough. Or maybe not even that. But let me formulate it in my case. Every omega strictly convex sufficiently smooth domain is spectrally rigid. And I can add a d in front of here. I'm asking what conjecture would be paraphrased as any omega is dynamically spectrally rigid. Which means that, again, I cannot deform it in any smooth way, preserving the length spectrum unless I have a trivial transformation, just a rigid motion. Now let me state the result that we have in this done. So I actually need, okay, fine. Theorem. This is a work in progress, joined with Alin Kaloshi and Sheldon Wade. It says the following: if omega is C7 sufficiently close to disk, which means that the curvature is essentially constant, the oscillation of the curvature is small enough, then any C1 smooth deformation of omega into another symmetric plane if it is isospectral, then it is isometric.
So symmetric is axially symmetric?
Yes.
It's a reflection. What do you mean, reflection?
So, leg would work. So if I take the deformation of this guy into another symmetric domain, then I will change my length spectrum unless I'm moving trivially with rigidity.
So is the deformation through a family of axially symmetric? It's not just the endpoint.
No, through. Right.
The isospectral family is isometric.
Yeah, it's a deformational result. I cannot leave my class. But it's, to some extent, we could replace, we could drop the, not the generosity assumption, the genericity assumption, because on the one hand, we work with the length spectrum, and so we don't have this problem of dealing with with different periodic orbits which have the same lengths. And on the other hand, we kind of dropped non-degeneracy because we could prove that, well, to some extent, we can work with only a limited set of periodic orbits, and those ones are indeed automatically non-degenerate provided that we are close to the circle. So that is our result. And again, it's a work in progress because it's not written yet, and we plan to get rid of this. But add back to the risk. Okay. We think we can do it, but it's not there yet. Thank you. Yes.
So the way you define these periodic orbits is through minimizing, as Jack pointed out, with minimizing L2 norm. And the way to define, say, the kernel of the Poisson is also through minimizing some other L2 norm. Do you know if there's any link between those two extremal problems and these questions?
I don't know exactly. I know that the proof of this is called the Poisson formula, the wave trace formula, or whatever. This one took a long time to be cooked up. Again, it was in the early 70s. It was proven for the closed manifolds, and it took 10 years of hard work. And all these papers are published in Nanas and Ziones, and there's a large step in each of them. And so it's hardly non-trivial to prove this. The equality is relatively straightforward once you have that generically again. But I'm not aware of any immediate relation between the two, except for the usual anyway thing that, oh yes, but you have duality between wave and particles. If you look at the wave thing, then these are the eigenvalues of the deflection, and if you look at the particle semi-classical thing, then it's going to be billiards. So it's the same thing. But it's better and maybe I don't think it's approved. Took a lot of work and effort to work this out.
By the way, George Birkhoff died in 44.
Okay, you checked.
Yeah.
Great. Yes.
So the axial symmetry here is just an artifact of the proof you.
No, it's quite substantial, in fact. We use it in several. Well, okay. Conjecturally, this is not needed. But to our surprise, it seems like this fact that it might be an artifact of the proof. However, if it were an artifact of the proof, it would mean that axially symmetric domains, in fact they're more generic, but they would not be spectrally rigid, because we can actually find a class of perturbation which, at least infinitesimally, leave every symmetric orbit with the same length. Which is by no means a counterexample of spectral rigidity, but it is quite strange. So I don't think it is an actual artifact of the proof. In fact, Zeldich assumes this very same thing for completely different reasons. So it seems to be there somewhere in at least the technology. We use completely different approaches. This work is substantially stronger than ours, of course, but it requires analytic domains. And the reason why it requires analytic domains, it's essentially, well, you can summarize it in 2 words, is that the Laplace spectrum, from the Laplace spectrum, provided that you have all these degeneracy conditions that you asked, you can obtain some information on the jet of the Birkhoff, the Poincare map for a very special orbit, which is the bouncing ball orbit, which always exists, and it is symmetric with respect to this guy. Now, if you know the jet of this map, you can reconstruct the jet of the curvature around that point. And since your domain is analytic, you're done. So this is very fundamental for this proof. So he essentially uses very little dynamical invariance and just uses one periodic orbit. And what we do is a much more dynamical thing. We use a countable set of symmetric periodic orbits, and those are enough to kill all perturbations which preserve the symmetry. But any symmetric orbit will not be affected by something which is in your orthogonal space to that. So again, it's still a work in progress, so it could go 2 ways. You can either prove that, okay, fine, we found a tiny perturbation which will open the possibility for a non-spectrally rigid domain. Or, well, no, maybe we can complete this argument and actually prove that, no, in fact, you can actually do it without symmetry. But there are several ways to kind of improve this statement. At the moment, as I said, we are working on removing the assumption of being sufficiently close to a disk, which is used somehow in a less fundamental way. And then we might think of seeing what can be done for non-symmetric domains. But that's an abstraction to say anything about it.
We can change Jacopo.